So we are on lecture 7-1. We're still doing AC power, and we're now looking at a new way of looking at it. If you have a periodic function, there is something called the RMS, or the effective value. All right, so the RMS value is an effective value for a periodic function. So the formula is that the RMS value is 1 over the period, the integral over 1 period, x of t squared dt. If you're talking about a voltage, that formula just becomes VRMS. And if you have a sinusoid, you go through and do this formula, and then using trig properties, whatever the peak value for a sinusoid is, the RMS value is always the peak value divided by the square root of 2. For sinusoids, there's a special formula, and you get it from doing trig properties on that formula above. So if I give you a sinusoid, the RMS value is always the peak over root 2, which we've already used in class before. Okay? If you have a power you're looking for a resistor, your average power is now VRMS squared over R, or IRMS squared times R. Those formulas should look familiar to you because they are the same formulas that we had for DC power, except now it's RMS. So the formulas are the same if it's RMS. If I gave you the voltage in a peak, it would be Vm squared over 2R, which obviously converts into VRMS squared over R. Or it would be Im squared times R over 2. So if it's RMS values, it's VRMS squared over R, IRMS squared times R. If it's peak values, it's the magnitude squared over 2, R. Or the magnitude squared times R over 2. Is everybody okay with that? So the RMS value is referred to as the effective value of a sinusoidal voltage or current based upon the fact that given an equivalent resistive load and an equivalent time period, the RMS value delivers the same energy to R as a DC source. That's what I was trying to say with the whole RMS thing. So the effective value relationship, the average and reactive value become, in terms of RMS, VRMS, IRMS, cosine theta V minus theta I. I've given you that before. The one we had before was VM IM cosine theta V minus theta I, or VM IM over 2 sine of theta V minus theta I. So complex power is now a complex number that is the sum of the average or real power and the reactive power, and it has the symbol S and the units of volts ampere. So far we now have power, which has units of watts, reactive power, this is average power, reactive power, which has units of var, and now we have S that has units of volts ampere. That's how we keep them straight. So if I ever give you one of these by the units, you should be able to tell me whether it was P, Q, or S. Okay? S is complex power. P is average power. Q is reactive power. The magnitude of a complex power is called apparent power, and it also has units of volts ampere. So how we write complex power is S equals P plus JQ. The magnitude of S is the square root of P squared plus Q squared. That has units of volt amperes, and it is also apparent power. So now we can represent these with a triangle where we have a real axis and imaginary axis. So if I have S equals P plus JQ, if Q is positive, that triangle has a lagging power factor because Q is greater than 0. Or if Q is negative, this triangle at the bottom has a leading power factor because Q is less than 0. Or If Q is equal to 0, it's resistive. It doesn't have a, well, power factor is equal to 1 if it's resistive. Remember what power factor was. Power factor was the cosine of theta V minus theta I. So if Q is 0, the power factor is a 1 because cosine of 0 is 1. Okay, questions? So the apparent power requirement of a device is designed to convert electric energy to non-electric energy. And it's important that it meets the average power requirement. So average power represents the useful output of the energy converting device, but the apparent power represents the volt ampere capacity required to supply that average power. Remember, we talked about that reactive power is just inductors and capacitors that charge and discharge as you're delivering power. So they require source power in order to do that, but they don't give any useful output at the other end. It's the average power, the resistive device that does that. So the other thing we could get from the triangle is your power factor angle. We talked about that before because you could get it from the impedance. And also that same angle shows up in the complex power and in the impedance triangle. So we can now use this triangle in our trig properties to solve for values, just like we did in our trig class. The main thing I need you to remember is Chief SOHCAHTOA. Did anybody learn that in high school? Anybody learned about Chief SOHCAHTOA in high school? Okay, so don't forget sine is opposite over hypotenuse. That's what so means, right? Cosine is adjacent over hypotenuse, and tangent is opposite over adjacent, okay? So I can give you these values in terms of the triangle by giving you angles or numeric values, and just by using trig properties, you ought to be able to find those other values. So the last set of formulas is, I can also find the complex power in terms of voltage and current by using VRMS, IRMS conjugate. The first thing I want to emphasize is that there's a conjugate here, because students will forget about that and think it's V times I like power was before. There's a conjugate. What does conjugate mean? The conjugate of A plus JB is A minus JB. The conjugate of a magnitude and an angle is that magnitude, and you flip the sign on the angle. So VRMS, IRMS conjugate means you flip the sign on the angle or you flip the sign on the imaginary part. Okay? The other formulas in terms of magnitude are 1/2 VM IM conjugate, or in terms of impedance, the magnitude of VRMS squared over Z conjugate. Any questions? I also have one to just find average power. It's the magnitude of IRMS squared times R, or the magnitude of IRMS squared times X. If Z is a purely resistive element, I can also use the magnitude of VRMS squared over R, or if Z is a purely reactive element, I can use the magnitude of VRMS squared over X. Okay? Now let's do some examples. I know that was a lot of theory. Remember, most times I'm going to give you the formulas on the formula sheet, but you got to know how to use them. So find the effective value of the voltage for the following repeating waveform. What this is saying I need to do is use the formula power equals VRMS squared over 5, or VRMS squared over R. So I need to find the RMS value for this voltage. So the formula is VRMS squared is equal to 1 over the period, the integral over 1 period, V of t squared dt. The RMS value is 1 over the period, the integral over 1 period, voltage squared, and then take the square root. So the first thing you're going to notice is that the period is pi seconds. Okay. The equation for V of t for 1 period is it is 5 volts between 0 and pi over 2. And then it's 2 volts between pi over 2 and pi. And then it repeats every pi seconds. Oops, sorry, that's a 4. Thank you, Alfred. That should be a 4, sorry. 4 volts between 0 and pi over 2, and 2 volts between pi over 2 and pi. So V squared of t is 16 volts squared between 0 and pi over 2, and 4 volts squared between pi over 2 and pi. VRMS squared is equal to 1 over pi. This is piecewise linear, so I got to do 2 functions. One integral is going to go from 0 to pi over 2, 16 dt, plus 1 over pi. The other one is going to go from pi over 2 to pi, 4 dt. 1 over pi, the integral from 0 to pi over 2, 16 dt, plus 1 over pi, the integral from pi over 2 to pi, 4 dt. 1 over pi times 16 times pi over 2 minus 0, plus 4 times pi minus pi over 2. And VRMS squared is 10. All of that just to get a 10. Okay, if VRMS squared is a 10, what is the power? What's the average power? If VRMS squared is a 10, what's the average power? V squared over R. It's 2 watts. It's 10 divided by 5. 10 divided by 5 is 2 watts. Okay, we have a waveform here, and it's a current, and it says determine the average power dissipated. Remember, dissipated, somebody asked me this the other day. Dissipated means absorbed. Okay, dissipated and absorbed is the same thing. Find the power dissipated in a 10 ohm resistor. Yes. So what we want to find is the RMS values, the RMS value. So remember, the RMS value for the current is going to be 1 over the period, the integral over 1 period, I of t squared dt. And I'm trying to find the power delivered to a resistor. So the power is going to be I RMS squared times R. It's IRMS squared. Oh, yes, it is IRMS squared. Thank you, Drew. This is IRMS squared. So IRMS squared is 1 over the period, the integral over 1 period, I squared of t dt. And the formula to find the power is IRMS squared times R. Okay, so this one you're given the equation already. So you know that I of t is 10t squared between 0 and 1 second, and then 0 between 1 and 2 seconds. I of t is 10t squared between 0 and 1 second, and then 0 between 1 and 2 seconds. Okay, same as before. Next, I'm going to square I of t, square I of t. This is going to be I squared of t. So that'll be 100 t to the fourth between 0 and 1 second, and 0 between 1 and 2 seconds. Any questions so far? Okay, what am I going to do next? What am I going to do next? Take the integral. That's right. So I'm going to have, what's my period? What is the period? The period is 2 seconds. So I'm going to have 1/2, but I'm going to integrate from 0 to 1 because 1 to 2 is 0. So it's going to be the integral from 0 to 1, 100 t to the fourth dt. So this is 1/2, 100 t to the fifth over 5, evaluated from 0 to 1. Find the power. We'll find RMS squared and then find the power. Find RMS squared and then find the power. Okay, we're going to go with 10. Everybody who did not get 10, please try it again. Okay, now power is IRMS squared times 10 ohms, which is 100 watts. 100 watts.